let's talk measures of variation now. So measures of central tendency are sort of where the middle is, and if you haven't watched that video of mine, go watch that one first. But then measures of variation are about how widely or densely spread the values are for the variable that you're looking at. And so we're talking about one variable at a time here. So the simplest measure of variation is the range. And so the range is something you can use for ordinal, interval, and ratio level variables. Anything that you can put in order, you can say what the lowest is and what the highest is. You cannot use this for nominal level variables because, again, you can't put those nominal level variables in any order because they don't have an order. They're just different, but you can't put them in order from lowest to highest. So the range is super easy. All you have to do is subtract the highest value, subtract the lowest value from the highest value. So if this is our example here, we've got a number line, we've got 3, 4, 6, 7, and 9 as our values. So we have 5, this is a sample of 5 values. Our range would be, we take the highest, which is 9, the lowest, which is 3, subtract them, our range is 6. So this is an important measure if we just want to identify what is the entire span or range of possible values. So in our sample, what is the highest and what is the lowest and how big is that span from lowest to highest? That's all the range does. But we get a little bit more, we want to know a little bit more about the measure of variation, then we would use what's called the interquartile range. The interquartile range this is your difference between the scores at the first and third quartiles. So essentially the range cuts out the problem of extreme values because all it does is it looks at the middle 50%. Because your quartiles, they correspond to, the first quartile is the first 25% of cases. The second quartile is the first 50% of cases, which would also be your median. The third quartile is the first 75% of your cases. So you're basically breaking them into 4. And so when you're looking at the difference between your first and your third quartile, you're cutting out the bottom 25% and the top 25%, and you're looking at the middle 50%. That's what the interquartile range does. So your first quartile position, so this is not the value, this is the position. This is going to be similar to when we talked about how to figure out the position of the median in the measures of central tendency. So the first quartile position then is you have to take your n, which is your total number of values, add 1, divide by 4. And then the third quartile position is you do that same thing, but you just multiply it by 3 because you want to get the position at the third quartile instead of the first one. So let me show you an example here. I'll bring up my wonderful paint again. So let's look at an example. So we got a set of, we'll say 2, 3, 5, 6, 7, 8, and 10. Gosh, this is not easy to do. Okay, so 2, 3, 5, 6, 7, 8, 10. So we have how many values? 1, 2, 3, 4, 5, 6, 7 values. So that's our sample size is 7. So the first quartile position, then we do the n plus 1 over 4. So our n is 1, 2, 3, 4, 5, 6, 7. So 7 plus 1 over 4, which is 8 over 4, which is 2. So that would be our second position. So there's our first quartile position. Then this third quartile position, we do 3 times that. So we do 3 times n plus 1 over 4. So we're doing 3. So that's still going to be 8 in the middle because n plus 1 is still going to be 8 over 4. Gosh, this is not. So we got 24 over 4. So then that's 6. So now we go 1, 2, 3, 4, 5, 6 position. So again, these are our positions. So to find the interquartile range, then you switch to the values. So now we're going to the values. I can switch my color. Why don't I do that? So our values are what we then use to find the actual interquartile range. So, all right, we found our values, our positions. So then the interquartile range is the third value minus or sorry, the third minus the first, so that would be the 3, is 5. So in this case, the interquartile range is 5. So that's sort of an easier one. Let's do another one where kind of, let's just erase all this and do it again. So we'll have our starting set will be 2, 3, 5, 6, 7, 8, 10, oh, I'm going to run out of room here, 12, and 13. So that's, say, our starting set. So now our n is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have an n of 9. All right, so the first position then is going to be our n plus 1 over 4. So I'm not going to write it all out this time, but we're going to see. So so it would be 9 plus 1, so it would be 10 over 4. So that's a value, so 10 over 4. So that's 2.5. And the third one then is just going to be, we multiply this by 3, so 3n plus 1 over 4. So then that's going to be, so 9, 10, so 30 over 4. And so that is 7.5. Okay, so now you're like, well, what do we do? Because we're at we get half positions. Well, what that means is your position is going to be halfway. So 2.5. So this is our second position, and this is our third position. So 2.5 is literally whatever is halfway between these two values. And then 7.5, we're at 1, 2, 3, 4, 5, 6, 7. So there's 7, and there's 8. So this. So it's halfway between 7 and 8. So then our interquartile range is going to be the third position minus the first, right? The third minus the first. So in this case, our third position is going to be halfway between 10 and 12. So now we're going to the values, because remember the interquartile range is the values, not the positions. So, well, what's halfway between 10 and 12? 11. And then what's halfway between 3 and 5? 4. So all you do is you subtract 11 minus 4, so then that's 7. So our interquartile range is 7. So now it's not always as easy to, if that is just going to be the number that falls between, but this is just an example. But basically, if these were sort of bigger numbers, you would then just find, well, what's halfway between? So you would add the two of them and then divide by 2. So you're just finding the where the halfway point is there. So that would be how we find our interquartile range. So hopefully that makes sense, because that we're going to move on to something even more exciting next, which is variance. And this is now getting into something that is going to be a lot more useful, because like the range is great, the interquartile range is great. It tells us kind of how big that middle value is, or else how big our entire sample is. But variance is now where we're getting into something where it actually is looking at all the individual scores and how much they all vary. So in kind of words, the variance is the average squared distance of each case from the mean. So what this looks like, and don't get scared by this is not as sort of scary as it might look. All this means is we're looking at, so this is just variance, that's just the symbol for variance. And this just means sum, so we're adding up, and we start at the first case that we have, and we go up to n, so however many cases we have in our sample. So for each case, we take the value of that case, which is what x is, subtract x bar, which is just the symbol for the mean. So we have to find the mean for our entire sample, and then we subtract each case from the mean, we square that difference, and then just add that up for all the values we have, and then we're going to come up with a big number. When we add all those up, we just divide that by how many we have in our sample. So in kind of words, you take each score, subtract the mean, then square that difference, then sum all those differences and divide that sum by n. So essentially what you're doing is you're finding where the mean is, and then you're taking each point that's plotted on, or each data point that you have, and seeing how far away is it from the mean. So that's the subtracting part. The reason we square it is because by definition, the mean is in the middle of all of our values. So if we were to just add up the distance from the mean of all of our values, and we didn't square it, then some would be positive and some would be negative, and you would get 0 every time. Because you would add up all the ones on this side and then subtract all the ones on this side, and then you would always end up with 0. So we have to square them. So that's why we square them, so that it gets rid of the negatives. And so we're taking each point. Let me bring up paint again. And get rid of all this. So essentially what we're doing is if we have we've got maybe we'll do a number line here. And so our mean is going to be right in the middle. And we have all these values here. And they're all a certain distance from the mean. So if this is our mean in the middle, then we want to take, so there's a point here and a point here. And we basically want to see how far away that is. Then how far away is that point? And then we've got a point over here and a point over here. Well, how far away is that point? And how far away is that point? And you're basically taking those distances, and so subtracting from the mean, because this is our starting point essentially. So you're seeing how far away it is, and then you just square that difference, and then you just add up this difference plus this difference plus this difference plus this difference, and so then you're going to get a big number, and then you just divide it by how many points you have so that you can see the average distance from that mean. That's really all the variance is, even though it kind of looks a little bit, it might look a little bit scary if you've never seen a formula like this before, but that's all that this is doing. And so then take it one step farther, and we use the standard deviation. And so the standard deviation then, it takes that variance. So this is the exact same formula that we just used, and it square roots it. So it square roots the variance. And the reason for that is because square rooting it brings it back so that the numbers make sense in terms of the values of the cases. Because if you're, for example, using something like the variance of age, then you're going to have, your variance will be the average squared years that people are from whatever the mean value is of your age. So if your mean value is the average is 20, so that means that in your sample, the average age is 20. Your variance is going to be, well, what are all the squared differences of, you've got some 19-year-olds, some 18-year-olds, some 22-year-olds, some 24-year-olds. And so you're adding up all those differences, but then squaring them. So the final number you get is actually the squared total difference of all your points from that mean. So square rooting it for standard deviation just brings it back so that you would say, oh, well then, the standard deviation is 2 years or 3.5 years or something, and it brings it back to the original numbers that make sense in terms of the case values. So all you do to find the standard deviation is take the variance and square root it. That's all you do, and this is overwhelmingly the most popular measure of variability. So very often you're going to see that well, here's the average and here's the standard deviation. And it's because it's the best measure of variation. And it also has some pretty cool properties where within a normal distribution, if you have a normal distribution, then you're going to have 68% of cases are going to fall within 1 standard deviation. So going up 1 and down 1 standard deviation. So between there is going to be 68%. Between 2 standard deviations is going to be 95%. And between 3 standard deviations is going to be 99.7%. And if you have a normal distribution, those numbers are always those numbers. So you can do some pretty cool stuff once you know sort of how many standard deviations out you are. So, for example, something like IQ, the mean and the median is 100, an IQ of 100, standard deviation is 15. So once you're at 115, you are 1 standard deviation above the mean. Once you're at 130, you're 2 standard deviations above the mean.